All right, I think we're recording. Thank y'all very much for coming to the Spacecraft Seminar Series, Introduction to Model-Based Systems Engineering. It's going to be a good one. I'm excited. We got some actual integrated system models, SysML, to show everyone. We're going to go over a lot of good stuff. So without further ado, let's get to it. We're going to talk about what MBSE is, and we're going to talk about the four pillars, if you will, of MBSE, although we'll talk about how that can be phrased different ways. We are going to talk about the application of it. We'll show an integrated system model. We will show how to use domain ontologies for the benefit of a spacecraft program. But it's model-based systems engineering in general, but the system of interest here will be spacecraft. And then we'll summarize everything at the end of each section and then again at the end. So first off, what is MBSE? In order to do this, we need to go through a little bit of recap from one of the previous seminars. So if you haven't looked at the Introduction to Systems Engineering, that's where this material comes from, and you should probably start there. So the big takeaway from that one was that we are all systems engineers, no matter if you're electrical, aerospace, mechanical, everybody is the systems engineer. So everybody, whether we know it or not, is implementing systems engineering methods. It's just a matter of how well you can contextualize your work within those systems engineering methods. All of this happens within a life cycle, and we can define our life cycles particular to the system. All of these systems have requirements. Many do requirements-driven development, but some, like the Mars Ingenuity helicopter, do not have any requirements other than, say, integration into the Perseverance rover, and they do capability-driven design. But in general, it's a good idea to have requirements, and specifications are generally those lower-level requirements. The goal is to advance the technology readiness of a system so that it can work correctly in its operational environment. We are shooting for technology readiness level 6 by PDR, except for those technology demonstrations that we're building or maybe haven't been flown or operated in their intended environment yet. 1 to 5 is done through development tests and analysis, and TRL 5 to 6, those are qualification tests, environmental tests in the extremes of the anticipated operational environment. So integration is really the most difficult part. What you do is you identify the subsystem specific technical performance measures, TPMs, and then you figure out which components realize those TPMs. You integrate along those chains to realize the TPMs, and you work backwards there till you have your full integration profile, knowing all of your integration points where things come together. Those points themselves, what are the things that we're developing. Verification and validation have 4 methods: analysis, inspection, demonstration, and test. Verification is, did I do it right? And validation is, did I do the right thing? And they have the same methods, but for different reasons. And here we work with 4 kinds of parameters. You just have regular parameters, and then you have important parameters that we organize as knowledge points. They're not necessarily controllable, but they're things that we care about. We're going to see examples of those today. Then you have technical performance measures, which are those knowledge points that are controllable, they're targetable, and they, as it says there, help us compare where we are in our system, our current performance, with our desired performance. And then finally, you have key performance parameters, which are system-wide technical performance measures, and there might only be 1 per subsystem, but these are your big things like your mass margin, your volume margin, your link budget, processor throughput, things like that for spacecraft. All right, so model-based systems engineering. We're going to have some formal definitions here, and I'm going to do my best not to read from the screen, but here I just want to do it for this definition. So it is the art and science of applying those software-based tools to capture systems engineering evidence in a systematic, disciplined way to connect system relationships, control system configuration, and communicate a common source of truth in the form of that integrated system model. So that what we hear, number 1, is art. There is an art to this. Just like Thomas Edison found 10,000 ways not to make a light bulb, we are finding 10,000 ways how not to perform model-based systems engineering. And it does take a good bit of trial in order to figure this out correctly, but there are right ways to do it. It's all software-based tools, and we're going to talk about formal languages, modeling languages, and those exist within the context of the software-based tool. And we're connecting system relationships. So you're going to see some things that MBSE can do that document-based systems engineering, DBSE, cannot do. And it's all about connecting those system relationships, and you have that common source of truth. What we have here, this integrated system model, can communicate to stakeholders, both internally, so we can represent material from the systems engineering team to discipline engineering teams. And we can also communicate the system itself to our higher stakeholders who need to understand if we're doing the right thing and are we doing it for the right reasons, validating the system itself. All right. So MBSE does not do systems engineering for you. If you can't do systems engineering, you're not suddenly able to do model-based systems engineering, because MBSE is a tool. It's a tool in the tool belt. It is just one thing that we can apply to certain systems engineering aspects, but it's not the entirety of systems engineering. You're going to take the different parts of systems engineering, technology advancement, integration, verification, all of the individual aspects, and you apply MBSE selectively throughout that. So it's a tool to be used to do MBSE, but it does not do MBSE for you. And we are going to draw the distinction between document-based systems engineering and MBSE. Remember, the point of systems engineering is not to produce documents, it is to make decisions. And that's what we're going to do here in a model-based environment. So what is a model? What do we care about that? As George Box eloquently said in 1976, all models are bad, but some are useful. Ryan, there's mark the tally. That's number one. So here is the DoD definition, Department of Defense definition of a model, and it's a pretty good one. You can draw a circle on a napkin, and that's a model of the sun. It's not a very good one. It's a bad model, and it's also not a useful model. So a good model is that it's descriptive and analytical in the sense that is defining the parameters, assumptions, methodology, results, conclusions of a given problem. It does not leave room for ambiguity, and it's going to take in information from many different sources. So it probably does not exist in a vacuum. It can be seen as a black box with lots of inputs, outputs, and interfaces. And we always model for a purpose. You don't model for the sake of modeling, or else you're doing something wrong. You need to understand what are the technical performance measures or knowledge points that you're trying to determine or ascertain as a result of the model before you even start. So plan the modeling processes. Thomas Gaskew gave the introduction to model-based system engineering for spacecraft, and he talks about that in there, how you should plan the modeling effort before you even start, and that's incredibly important. So here are the 4 pillars of model-based systems engineering, according to Bruce Chesley and Jerry Sellers, who are incredibly wise in the wide world of model-based systems engineering. Let's start here. You have an architecture framework, which we're going to talk about in depth, which says, what are all the things that I need to do from start to finish? What are all the products that I need to make? And there's a lot of different ways to talk about that. A process framework says, how are those products matured over time? What order do I make them? What's the maturation flow of those products? To what reviews, which stage gate reviews, do which products need to be shown? And what maturity do those products need to be when they're at those reviews? You have a modeling language with a defined syntax and semantics, where you have expressions in the modeling language, and the syntax is how those expressions are structured, and the semantics is what those expressions mean when they are structured that way. Finally, you have an ontology, which is a taxonomy of entities. So think kingdom, phylum, class, order, family, genus, species, but there's relationships between the entities in that taxonomy. Okay. So Thomas Gaskew, in his intro to MBSE, defines the 3 pillars of MBSE specific to the modeling language section. So don't take it as, oh, there's 4 pillars and those don't match up with these 3 pillars. It's just ways to conceptualize this, and none of them are necessarily wrong. I find this one to be a very high level, useful organization. So we're going to start here, but there's more than one way to approach this. So why do we do this? Why make things harder than they have to be? Well, it's those connections between system elements. That's not something you can do on paper. It doesn't work in document-based systems engineering, because if you have 7 different documents and they're all referencing each other in an ad hoc way, well, you're going to have to keep up with version control there. So we, in a model with a refined syntax and semantic structure, define aspects of the domains, physical operations, behavior requirements. We can manage configuration. So if an aspect of the design changes, or you want to evaluate what might happen if you change part of a design, you can see how it propagates throughout the model just by changing that one thing. If you want to integrate multiple models, it's possible through that top level integrated system model. If you have a MATLAB model, that can output directly into the ISM. So it's incredibly useful when you are organizing models in this centralized way in your digital engineering environment. This whole thing, all systems exist to communicate value to stakeholders. So we're going to use these models to communicate to our stakeholders, both internal, our subsystem technical engineers, our discipline engineers, and our external stakeholders, the people we owe and who give us lots of nice money. Okay. So what we're working towards, we know what it is, what the value of it is, what it does, and what it doesn't do. But what we're working towards is model-based reviews. How many times have you sat through a PowerPoint presentation that was incredibly boring and didn't give you the value that you were looking for out of it? Maybe you're watching it right now. This can be avoided with model-based reviews. When you are evaluating a system in a review, you can use the integrated system model, and you're not doing a PowerPoint. You're looking at the model. And that only works if you structure your models appropriately. But all of this information, the which artifacts can be generated, which ones are at which reviews, where do they come from, it's all in this integrated system model. And that's what we're going to talk about today, the working towards model-based reviews in a holistic sense. So please stop me if you have any questions. I'll keep going on forward, but if you got anything, just throw it at me and we'll keep going. All right. So this is the architecture framework, and we're going to describe things pretty broadly in the parlance of ISO 24765 at first, which is vocabulary for software and systems engineers. But at its core, an architecture framework defines all of the products that can be made to describe a system. So you see these architecture description elements, AD. The architecture description is just a way to describe an architecture. And in general, those take the form of products, things we have to make. If it is an analysis or a test that we have to do, we have to report on that. If we need to make a plan, a systems engineering management plan, an integrated system model, or a work breakdown structure, or an organizational breakdown structure, those we call products. Those are the same thing as these architecture descriptions. We are describing the architecture. And people often misuse architects, designers, and engineers. Those are 3 different jobs. So these architects define those rules for what the system does. The designers create solutions. Remember, architecture is the what, design is the how. Systems engineers, all of us, usually have to do both. You're solely going to be defining architecture or design. You're usually starting with architecture and moving to design. Wonderful. So here's a couple of those formal definitions. I won't read these out specifically, but your architecture is how that system is organized, and the architecture descriptions are products that can be made to characterize or express that architecture. The architecture framework describes all of the possibilities for those products. It's not what you should do, it's what you can do. So that is the formal definition of an architecture framework. And there's a lot of different ways that it's described, but it means a very specific thing. I hear architecture framework used colloquially, and sometimes, you keep using that word. I do not think it means what you think it means. I get that a lot, or hear that a lot. So all of these products that you're making, these architecture descriptions, can define whatever you want. It can be about the system, those 4 domains: physical, behavioral, operations, requirements, but it can also be about the enterprise. It can be about the management, or how systems engineering does their work, about how we're going to interface things, your interface control documents. What's the process for integrating these? Those are often very tailored to a given system, and they should be. So you do need to assess, you need to make this distinction of what are the things I can do, and whittle those down to what are the things I should do, which we're going to talk about now. Here is that formal definition again, because this does get a little bit tricky. It's kind of hard to follow in places, but we are taxonomizing all of the products that could be made. And remember that ontology part of this, the first part of an ontology is a taxonomy. So all of the products that exist should, in an architecture framework, should also exist in that ontology. That's an important part of this. So we're going to talk about a couple of architecture frameworks here shortly, but the big takeaway is this is a taxonomy of all of the things, all of the products or architecture descriptions that could be made to describe an architecture or system. Why do we do this? For management. These are incredibly complex systems that we're developing. If it was easy, we'd go do something else because we like a challenge. But it's hard to take that organization of, here are all the 2,000 things that I could make in this organization, in this execution of a system architecture, and whittle that down into the things that I should do and represent those cleanly. It's not an easy task. And so it helps management figure out, here are all the things that I need to do throughout the entirety of the mission, regardless of phase, to ensure mission success. That's what we're doing here. So when we do this in an ISM, it does help us communicate that picture from a central source of truth. It all lives in one place with integrated models from MATLAB or C++ or whatever into that ISM. Okay, so here are some examples of architecture frameworks that already exist. The big one that I want y'all to be aware of is the Unified Architecture Framework. This had a lot of precursor elements. You have you previously had the Department of Defense Architecture Framework, which you can see is the second bullet there. And then there was the Ministry of Defense Architecture Framework, which was what Britain had. So the US DoD, that's DODAF, and the British Ministry of Defense, that would be MODAF. And there was this thing called the UPDM, the Unified Profile for DODAF and MODAF, which is a lot of acronyms, I know. But then the UPDM eventually evolved through various iterations that we don't have time for into the UAF. And the UAF helps different countries, in entire countries, communicate systems between each other in a way that is rigorous. It has defined syntax and semantics, and it avoids ambiguity. That it is all wrapped up into the same central tenets. There is one for NATO. NATO actually absorbed the Ministry of Defense Architecture Framework. So all of NATO, when they're describing their missile systems or their communication systems, they're describing these using the NATO Architecture Framework. And if you're going to be doing engineering work for NATO or for a government body, it's highly likely that you're going to need to know DODAF and NATO Architecture Framework. Canada's got one, Australia's got one, and enterprises have some too. 60% of the Fortune 500 uses the Open Group Architecture Framework to communicate goods and services and enterprise structures. So this is not just something that we do to build missiles and to kill people in acts of war. This is something that all businesses should be doing. And MBSE is very clearly the future. And INCOSE knows the International Council of Systems Engineers, and so do the Fortune 500. So it behooves you to understand what exists out there. And you can see here are some that are ubiquitous, that are for military purposes specifically, and for businesses. Any questions on this? This is a very confusing section. All right. Moving on. So let's talk about the UAF a little bit more. I'm not going to read this off, but these bolded parts, this is how the object management group describes it. These strategic capabilities, operational scenarios, blah, blah, blah. It's a standard representation of all of these things. It enables us to model them, and you are able to standardize the way you communicate to your stakeholders, because these systems only exist, businesses, countries, military structures only exist to deliver value to stakeholders. And I think you can hear that the customers would be the stakeholders for the businesses, and citizens would be the stakeholders for a country's military enterprise. Okay, so here's a bit how the UAF works, and I know it's been a lot of text so far. You got a visual aspect of this coming up. It's broken into two parts: the domain meta model and the unified architecture framework profile. We're really only going to talk about the DMM, domain meta model, here, because it defines domains and model kinds, which you're going to see on the next slide. And these domains, there's a lot of different ones. And these are not the same as the physical operations, behavior, and requirements. They're a little bit more specific. And so when we say there's the NATO architecture framework, there's the UAF, there is the Department of Defense architecture framework. They organize these domains all a little bit differently. And then you have model kinds, so that you have this taxonomy, structure, processes, constraints. The combination of a model kind and a domain gives you a product. Okay, so here's what that looks like. The combination of a model kind up here and a domain here gives you a product. So this is, in a way, defining all of the different products that could be made to describe a system. But if I'm building an autonomous software system that does not require a pilot, I may not need personnel for interaction scenarios. So this might be an example for a given system that I don't need. I don't need to make this product to define my mission architecture or to ensure mission success. So all of the products that could be made, architecture framework. A mission architecture framework defines the products that should be made. It is the subset of the architecture framework that is relevant for your system. And when you whittle it down from the architecture framework to the mission architecture framework, that mission architecture framework, the products in there go into your work breakdown structure. The products in your mission architecture framework and the products in your work breakdown structure are the same. They're just represented differently. And they are all architecture descriptions, ways to express your architecture. So, distinction between AF versus MAF, incredibly important. And this is not something that is well known or well popularized. This is, it's a new thing. People are starting to realize that when you organize it this way, you can move faster and make decisions more effectively. There's different mission architecture frameworks that exist. NASA has released a space mission architecture framework, which we'll see next, and these are for uncrewed robotic missions. So this is what that looks like, and you can see that it's much different from the unified architecture framework. What they've done is they have organized their stakeholders, and then internal stakeholders or participants. They've defined viewpoints and then subsidized those into or subdivided those into views. And then you have view products. So view products existing under views, existing under viewpoints, and those all exist within a given stakeholder set. And I got to tell you guys, I don't love this. I think it is not useful. I think, all models are bad, but this one is not useful. Number one, this requires you to define a single stakeholder and allocate that to a single viewpoint. And it's because they put viewpoints in the middle of this, where you can't have a view product without a viewpoint. And that's an unnecessary limitation. Viewpoints are something that should be used to sort products at the end, and products should be able to fall under multiple viewpoints, and stakeholders should be able to care about multiple viewpoints. It's something that should be sorting after the fact. When NASA did this, like from my perspective, this was a swing and a miss. I know that this is just their baseline, it's their first version of this document, but if you read the document, it reads as if whoever wrote the second half did not read the first half. So there's a lot of different ways to do this. And remember, we're figuring out 10,000 ways how not to make a light bulb. This is way 705. Okay, so to summarize, architecture framework, all of the things that you could make, it is regardless of mission phase, all the things that I could do to ensure mission success. You can break it down into view products, views, and viewpoints. You don't have to do that. The mission architecture framework, that's the subset of things that you should do. And that's a really important distinction that we're going to carry through the rest of this digital engineering seminar. All right. Any questions here? We're going to move on to process frameworks. All right. So process framework. This has to do with how we are iterating on those products. Okay. These define which life cycles could we apply. Are we doing the NASA single project life cycle? Are we using the DoD 5000 life cycle? Are we using the WASN life cycle? There's a lot of different ones that you could use, which define what kind of reviews, which stage gate reviews. This helps you define your requirements. It helps you understand how you're going to integrate things. We are going to make that same distinction where you have process frameworks, or here are all the things that I could do. Here's all of the life cycles that could be applied, versus the mission process framework, which is this is the life cycle that I am applying. These are the integration and verification strategies that I'm going to implement. So this is not something that's been defined nearly as much as architecture frameworks. Architecture frameworks, you have the UAF, TOGAF, NATO architecture framework. That does not exist for these process frameworks. It's much more nebulous, and we're going to try and assess and debunk a little bit of the vagaries that exist for process frameworks here, but it is how we are iterating all this. So what's in it? Number one, that life cycle. You have to know what reviews you're going to be preparing for, what review data packages you need to make, what is going to be the integrated master plan, the schedule for your system. And that integrated master plan is in fact a product that exists in the mission architecture framework. So how are we going to mature each of these products over time? That is a big deal. So NASA has a variety of ways that they mature these products based on whether they're configuration controlled or non-configuration controlled, and that's in NPR 7123.1C currently, and we'll talk about that here in a second. But you need to understand, what are the kinds of products that I have? What are the maturation steps of those products? And we at the ACSI have defined our own version of this, which we're embedding into our mission planning tools and our analysis methodologies. But you have to know how you're maturing the products, which products are shown at which reviews, what product maturities need to exist by which reviews, which stakeholders need to exist at which reviews. This is something that we assert here should be in the process framework. That NASA Handbook 1005, the Space Mission Architecture Framework, they tried to put the allocation of those products to reviews in the same architecture framework, and don't do that. You should be combining your MAF and MPF in a holistic sense, and we'll show how that works as well. So the process frameworks also have to do with how you are defining and allocating your requirements, and how are you implementing some of your analysis and test procedures. It is process oriented. Okay. So what are some examples that do exist? NASA NPR 7123.1C. This is NASA's big systems engineering document, their guideline for how these processes work. And NASA considers that to be its process framework. But remember, we drew the distinction between model-based systems engineering and document-based systems engineering. NPR 7123 was built for document-based, DBSE. And it is all about, here are the documents that you need to produce, here are the things that you need to make, which in general is part of the architecture and process framework mentality, but it's built for DBSE. And so when we try and apply some of our model-based systems engineering content, it may not be as useful to us. So some people are the folks that created those 4 pillars of MBSE, they consider SE itself to be a process framework because it does include all of those topics that we've been considering. What are the requirement structures? What life cycle do we exist under? But that's also not a great answer, because historically, a lot of our systems engineering has been document based. We create system architecture specifications and system design specifications and development and integration plans and subsystem analysis plans. We have all of these documents, and a lot of those SE principles are just going to tell you to make more documents. And that's not what we're going for here. Remember, the goal is model-based reviews, communicating to your stakeholders in a centralized common source of truth. So if we are going to do that, how can we achieve that if what we know is not quite organized for model-based principles? Okay. We have to organize our MAF and MPF in a way that coalesces into your integrated system model. Okay. You have to understand your products within the context of that integrated system model. You have to understand the maturation philosophy, what maturities exist for what types of products. You have to understand what are the types of products that you have. In the ACSI, we have 6 different products. We have models, software, hardware products, design products, plans, and reports. And each of those have individualized maturation statuses. And those are defined in our mission process framework. And we did that so that we can organize our integrated system model. The number one thing that you can do when you know what is in your MAF and MPF is describe which products are artifacts and which products are non-artifacts. Okay, what does that mean? Artifacts are things that are generated from the model. They come directly from the integrated system model. So this can be a figure, it can be a process flow, like a state machine, or it can be a Word document. It can be an Excel spreadsheet. Those things can be generated from an integrated system model, the Word document specifically using the velocity template language, which is an incredibly powerful tool. The non-artifacts are generated by discipline engineers. So CAD might be a non-artifact. You might have things that start as an artifact in one review, say an interface control document, and then as you progress to the next review, it becomes a non-artifact. So not only do you need to know which products are artifacts and non-artifacts, you need to know that at which review. So if I have 8 reviews and 100 products, I need each product to be known what it's going to be, artifact or non-artifact, who is producing that product at which review. And if we can do that, it's going to reduce the amount of time it takes to generate those products in a review data package provided to the stakeholders before the review. So this combination, understanding the maturation of your products, understanding if the products are coming from the systems engineers to the integrated system model as artifacts, or understanding if products are coming from discipline engineers through discipline engineering, electrical, aerospace, whatever, as non-artifacts. And if you know those, you are enabling model-based reviews through the combination of your mission architecture framework and mission process framework. Any questions there? That's an incredibly confusing thing. Brand new systems engineering, hot off the presses. All right. So to summarize, mission process framework, all of the processes that can exist, all of the different life cycles you could choose, all the different maturation statuses, all of the different product categories, that kind of thing. Mission process framework, all the things that you should do. What is your life cycle? What are your product categories? What are the maturation statuses for those product categories? How are you allocating products to those stage gate reviews? Which products are artifacts or non-artifacts? based on which review they're being shown at. All right. Pressing on. So modeling languages. We're going to actually show the ISM here in this section. So we're going to draw a distinction at first between a natural language and a formal language. I am speaking a natural language. Some might argue I am speaking it poorly. It is loosely defined. It might be ad hoc. I might throw in some Southern dialect, y'all. Something like that. You can do it however you want, as long as it communicates your point. Some Southerners I grew up with could speak all they want and not communicate their point. A formal language is at its core machine readable. It has a specifically defined syntax and semantic structure. Again, syntax is how an expression is structured, and the semantics is what an expression means when it is structured that way. All right, here is that definition, and we'll of course post these PDFs and you can go through those. So I'll read it. Here are the formal definitions for syntax and semantics, and the combination of these defines a modeling language. And we are here specifically going to talk about two modeling languages: the unified modeling language, UML, and SysML, the systems modeling language. So no matter what modeling language you're using, this is in general the structure that it takes. All right, we have something here that we are trying to model. It looks like here it is some factory or greenhouse gas polluting something, but it is controlled by some centralized controller, some computer hardware. It's implemented by these people. It interprets all of these different kinds of data and processes, and then it's implemented by people actually doing or controlling it. So you have something, some abstraction, and people who are actually going to use it. So this abstract syntax up top, this is what exists behind the scenes. People are not supposed to be interacting on a daily basis or on a minute basis with these background processes, the semantics. You're supposed to be using a language, moving around blocks, making different diagrams. And as you create those entities in the model, it is in the background automatically doing the syntax and semantics. So you're not interacting with that directly. You are using the language, and that is getting translated into the syntax and semantics, much as we use a programming language that then eventually becomes machine language, that kind of thing. So we're going to manually use these tools, and it will automatically generate things using that syntax and semantic structure. All right. So SysML here, what you're going to see shortly, is an extension of UML, the Unified Modeling Language. UML started informally with software engineers, but it was quickly picked up by hardware. It's not only software. This was in, I believe, the early 80s. It went through a couple different versions, and people argued about what kinds of syntax and semantics and things you could do inside of it, what that should be. And they used it to describe a whole lot of systems. But some people who were doing systems engineering thought that it wasn't good enough. It did not have certain things like requirements organization, and that you couldn't do parametrics. You couldn't do math in the language. It is just modeling and a system architecture and system design. So SysML extended UML and added some stuff to it. It took some stuff away and it added stuff to it. And you have the structure of a system, you have the behavior of the system, what that system is doing, what are the requirements of the system, and then what kind of math. And you don't always have to have the math, but it helps. Here are the 9 diagrams from SysML. Okay, they're all in SysML. You have a block definition diagram that is system architecture, that defines what the system structure is. Internal block diagram is all about interfaces for that system or subsystem or component. Package diagrams are effectively just like a fancy directory. It is the same as your file system, where you're just packaging things inside of it, but you can also make effectively zips, where you're just sending a package to someone. That's a small subset of what you want to do. Behavior, there's 4 ways to do it. Activity diagrams are nice. You can show process flows. We'll show a little bit of that. Sequence is more advanced than activity. A sequence diagram can show who invokes behavior, whereas activity diagrams cannot. A state machine is more top level, and that is generally going to invoke other sequences as part of the do, the entry, do, and exit behaviors in a state for that state machine. And then finally, use cases, where a use case is how a user, an actor, is interacting with the system. It is invoked by an outside participant. Behavior in general, whether it is a chronological or environmental stimuli for the system, that is not a use case. That's just a behavior, but both behaviors and use cases can be defined through scenarios. And scenarios can be defined by activities, sequences, or state machines. Yay. Finally, you can organize your requirements, and then you can do some math inside if you want. But sometimes, remember, we don't model for the sake of modeling. Sometimes we do that math in MATLAB or Thermal Desktop or another kind of model. So it's not always best to do the math in SysML. Generally, for your easy math, like mass roll-up patterns, where you allocate masses to lower level components, then it rolls up to the top level, which is nice. We do that a lot. Okay, so now let's go actually look at the model. We're talking about MBSE. Let's look at MBSE in practice. Okay. So I think everyone can see this. Yeah. Noah, are you good here?
Yeah.
Okay. So this is a model. It is a bad model, but it's a useful model, I think. George Box might be proud. You can organize your model a variety of different ways. The way that we are organizing it, and we're not quite done, is based on a military standard. I want to say 490. I'm probably wrong. That should be double checked. But here you can see a variety of ways to look at the model. And remember, the goal is model-based reviews. You want to set up all of the review data package material, all the stuff that your stakeholders care about. Remember, we know which stakeholders are attending a review, and we know which products represent the concerns of those stakeholders. So those products need to be shown at that review. So you can represent all of the products that you need to show at a review in a hierarchy that looks something like this. I know it's a little bit jumbled at the moment, and again, we are not finished. This is a work in progress. So you can look at something, a very high level thing like the mission architecture. All right. So here might be a little hard to see. Let me see if I can zoom in just a hair. So here you have a ground segment, the mission operations center, and the ground control station, and the spacecraft. So this is just the context that the mission lives within. Very simple, very high level. Doesn't necessarily have to be something incredibly complex. So then that was an IBD of the mission architecture. I can look at, here is this block definition diagram. Mission architecture is comprised of the spacecraft architecture and the ground segment. So what's going into space, what stays on the ground. If I want to look at the spacecraft architecture, here that is. So the spacecraft is subdivided into spacecraft hardware and flight software. Flight software has its own, I can open this in a new tab. I'm not going, I think I can just double click it. Yeah, so here is going into this nested flight software diagram that has all of the components of that. These are all block definition diagrams here. Spacecraft hardware is divided into the bus and the payload. And then the bus, you have the subsystem for the bus. And these all have their own individual subsystem block definition diagrams, structures and mechanisms, thermal control. I mean, I think I can go into this one, and this one's way too big. I mean, this is something that I'm working on subdividing, and you can see there's a whole lot of stuff involved in this block definition diagram. This is not a useful model. This is not something that you would want to show without refinement to stakeholders per se, because it's hard to read. You have to be able to communicate the value of the system to stakeholders. Cool. All right. So we've looked at the spacecraft architecture, and then maybe we'll look at the ground segment. So here's some aspects of the ground segment, and we still have a lot of work to do here, but this is communicating the system architecture. Okay. So that is just the system itself. Let's think about this conceptual physical architecture. This is an internal block diagram. So this is defining the interfaces within the spacecraft itself. What's happening with G and C and telemetry tracking and command? What's happening with command and data handling that is interfacing with the flight software, thermal control, electrical power system here. Thomas Gaskew in the MBSE for spacecraft has a much better version of this. I highly recommend y'all go look at that. We are actually in the process of emulating the diagrams that he had set forth there. Okay, so now, importantly, this is all about the structure itself, the architecture, but that is just one domain, the physical domain. What about the requirements of the system? So let's look at the performance specification. This is something that can be communicated to stakeholders. Remember, we're not just getting into a PowerPoint, we're actually looking at the model and going through it. So this is that military standard, this 1 through 6, the scope of this performance specification. And right now, this is set up for the entire spacecraft. But what you want to do is to create this for each of your subsystems. And that's what we're working towards right now. Define this for each subsystem. So applicable documentation, I can go over here into the containment tree. And let's say I open up, here are all the specifications, standards, and handbooks. Here are all these NASA standards, NASA procedural requirements, procedural directives, non-government, all kinds of stuff. And I can just double click these and open this, which is a really powerful thing. So then I can look at, here are all my actual requirements. So let's take a look at those requirements themselves. Here are the requirements in the system. We're still working on these. Don't take them as truth. We're going to be getting these out to all the subsystems here come the next semester. But remember how we said that the advantage of MBSE, one of them over DBSE, is that you can connect system entities. So what we've done is we have defined a requirement. This requirement is satisfied by the existence of this subsystem. This requirement is satisfied by the existence of this component. This is who owns it. This is the verification method. So if we know what we're verifying our requirements as, let's say this one is verified by analysis, we are then going to have to create a model for that. So then we can make a, let's go back to the performance specification here in quality assurance. This is my requirement satisfaction matrix. So I know which entities in the model are satisfying which requirements. And if I have a requirement that's going to be verified by analysis, I need to satisfy that requirement using a model. So right now, all of our discipline engineers are organizing inputs and outputs from their models so that we can represent the model in here, not just reinvent the wheel, not redo all the model stuff from MATLAB or Thermal Desktop or whatever, but we can represent the model, show its inputs and outputs, link those inputs and outputs to either our environment or to spacecraft parameters. And then we can say, okay, this model is analyzing this technical performance measure and it satisfies this requirement. So this is the utility of model-based systems engineering that document-based systems engineering can't hold a candle to. So when we say this is the future, this is what we mean. All right, so that's some of your requirement satisfaction. This is a longer form requirement traceability diagram. So this is effectively just showing, and you would not show this to stakeholders, which requirements are derived from which requirements. You can see all these requirements come from higher level requirements, most of them do, and this is the same thing as this right here. So I know that this requirement is derived from this ACSI L3 bus 15, this one. They're linked together. So even if I change the verbiage of this one, it will change down here as well. So requirements traceability, incredibly important. Let's go back to the model navigation here. Again, this performance spec should exist for every single subsystem. We know here, we can organize our technical performance measures. We know exactly who has them, who is responsible for these technical performance measures, and these can be either generated in the model or reported from discipline engineers as part of the non-artifact representation within the integrated system model. And here are the types. Here's those units. So incredibly powerful stuff. And we can, of course, do this for key performance parameters. Remember, key performance parameters are just a subset of the technical performance parameters or technical performance measures that have to do with the entire system. What do we care about most at the top level? Key performance parameters here. All right. So here's a little bit about traceability. Formally, you should define your stakeholder needs and translate those to requirements, which is, I guess we'll just give this a look right here. This is all just stakeholder needs. They were written out in textual form, and then they are allocated to one or more requirements. So we know that we are addressing all of our stakeholder needs by defining requirements specific to those. And remember, the stakeholders are going to give you needs in the voice of the customer, and we are in the voice of the user, the actual engineer. Finally, here are some risks. This is going to be low classification risk, low likelihood, low consequence, that kind of thing, moderate risks, and then high level risk. And this is just a visualization method. So if I wanted to look at this one, I'm not actually sure it's going to open if I do it that way. But if I look here, no, I don't know that it's going to show me because it's locked right now. Okay. Yay. Model navigation. Set this up for each review based on what you want to show the stakeholders. Organize it so that it is easy to navigate. You know, if let's say they ask something that is outside the scope of what I've prepared right here, let's say they ask about integration. Well, okay, you want to know about integration. Let's go look at it. Here, we have our master integration flow for how we're integrating the spacecraft, where these blue are function tests, the yellow is integration test, and the red is environment test. So if I wanted to look at this more closely, we know at the very end, here as we're flying, we're going to do a proto-flight post-vibe checkout test. Here is where we're vibrating the whole system. We're doing a post-bakeout checkout test, where we're baking out the whole system. We are integrating into that final proto-flight integration, so we're working backwards here. Here we're going to do integration of these structures and mechanisms, and here we're just doing the avionics, the actual brains and power of the spacecraft. Okay, well, then we're breaking that down a little bit further. You can see here, maybe a little bit, this is the development A, structures and mechanisms, and development A, avionics stack. These things have to be finished before it continues on to here. And we would move back. So you're effectively just tracing through what your stakeholders might care about. And we're in the process of working out the integration profiles for individual subsystems at the moment. So we would effectively just put an activity here with a nested activity diagram in and of itself. And there would be a little rake symbol on that activity diagram. Any questions? Oh God, this is bad containment tree, but we'll fix it. Any questions about the model itself? Utility, communication, what your subsystems are doing relative to this. All right. Let's move on. So to summarize, we're using formal languages, but we are not ourselves interacting with the syntax and semantics. We are defining structures of the system. We are defining behaviors. We're defining requirements. And then we're linking all of that together. And that's possible using the formalized modeling languages with the machine readable language. It's a formal language. And we do it to avoid ambiguity. And when we avoid ambiguity, we communicate to our stakeholders more effectively. Wonderful. Let's talk about ontologies. This part gets tricky. All right, we're going to try and go slow. So what we have here is an agreement on the way we speak. It's a very specific agreement. We know all of the categories that exist, the concepts that we could be interacting with, and we have formalized relationships between those categories, okay? And you can express this in a variety of ways. There are ways to build ontologies using the web ontology language, which is OWL, not WAL for some reason, and a resource description framework, which is ontological triples, which we'll talk about very soon. Finally, you can do this in SysML using extensible stereotypes, but that is not the way the authors of SysML intended you to do it. The authors of SysML did not anticipate how often people were going to make stereotypes. You're not technically supposed to be making your own stereotypes without a really good reason. I think in the entire time I've used SysML, we've only ever tried to make one stereotype for a product breakdown structure item. Okay, this is the hierarchy of semantics. So at the bottom, you have a list and then a glossary, some kind of loose hierarchy, a thesaurus, which is interesting, taxonomy, so kingdom, phylum, class, order, family, genus, species, tree of life, and then an ontology. An ontology is that taxonomy with relationships. That's the big thing, okay? The ontology is at the top, but it should apply everywhere, turtles all the way down. Okay, if you have something at the bottom that is breaking your ontology, something's wrong. Either the ontology is not correct or something at the bottom is not correct. All right, so it should be realistic and applicable the entire way down. What we're doing is defining ontological triples, or sometimes semantic triples. And these have a subject, an object, and a predicate. All right, so products reflect the concerns of stakeholders. We know which products go to a given review. Stakeholders care about those products, ergo, those stakeholders should be at that review. Those are the kinds of formalisms that we can apply if we've defined our ontology correctly. And the great thing about this is that if you do this correctly, it can be made to be machine readable. It can be interpreted as part of a formal language, okay? And we're going to use object-oriented programming languages to do that. So again, all models bad, some are useful. Ryan, that's 2. No, that's 3, I think. An ontology is a model. It is a specific rigorous model, but it's still a model. Aristotle tried to do it first. Thank you, Ryan. 4. I'm at 4. Keep it up. I think the over under 7.5. The Aristotle tried to do it first. In categories, he created 10 categories, and I don't know them all off the top of my head. I mean, they were eating moldy bread, so don't take their word as truth, but some of it was pretty good. And then in 1606, Jacob Lorhard popularized the term ontology. So this concept has been around for a long time, and it's often considered very meta. You know, it's the concept of everything. You can ontologically taxonomize anything, and you should, and everybody did start doing it because Protege came out from Stanford in the early 2000s, I think 2001, 2004, and everybody started making ontologies. And that was widely regarded as a bad move because you had ontologies that about music, about instruments, cars, anything at all. And so they were taxonomizing stuff and then creating relationships, ontological triples between them. And the problem was that you had one ontology and another ontology about something completely different, but you couldn't combine them. You could not, they didn't have the same structure, so there was no way to integrate those two ontologies. So what a guy named Barry Smith, and a lot of people worked on this, but Barry Smith in particular did a lot of work on this. They've defined and formalized a top level ontology. And an example of a top level ontology is the basic formal ontology. ISO 21838-1 and 2. That's where you could find these. And here is what the basic formal ontology looks like. This is, it starts with continuants up top, and continuants are things that exist. They have come to be. So you have independent continuants, which might be something like an arm or a drink or a head. And we'll skip over to specifically dependent continuants. And these are things that exist, but they depend on other things. Barry Smith likes to say that you can't have a headache without a head. So it is a specifically dependent continuant that exists as a function of something else, not as a function of ontologically, just it exists because the other thing exists, or it is able to exist because the other things exist. It's all very philosophical. That's why some people don't love ontologies in general. Generically dependent continuance is data. They are things that can exist, but they can exist in the same way multiple times. So a lot of information content entities are going to exist under generically dependent. Just to give it a little bit more, material entities, you can have objects or aggregates of objects like 5 apples or the Beatles, things like that. A fiat object part, if I ask you as a part of a cow, which part is the filet mignon, which part is the flank steak, they're not, not a real distinction, but they're things that we've come up with. Continuant fiat immaterial entities, continuant fiat boundary might be something like a state line or a divider of a country or the prime meridian or the equator. It's things that don't really exist. It's just something that we have prescribed as a boundary. Sites, spatial regions, that kind of thing. Specifically dependent continuants, they include qualities, things like colors, and realizable entities of role. I am a person. I have assumed I am the bearer of the role of lecturer at the moment. So these are just the ways that you can describe certain things. So this top level ontology for things that exist. So if everybody builds their ontologies, starting with this at the top, then we can combine ontologies. That's the point here. Occurrence are things that happen. You have processes, boundaries to those processes, like a start and a finish, spatio-temporal regions, and then just temporal regions, one dimension, temporal regions, starts and finishes, that kind of thing, and then instance within those. Okay, so top level ontology, a little bit difficult, but it's things that exist and things that happen. And when you organize your ontologies underneath this, you will be able to combine it and have multiple people working on them at one time, which is nice. So here are 4 steps for using ontologies. Just like in the modeling language, we should not be interacting with ontologies at the user level. These are things that should exist in the background, defining the rules for the syntax and semantics. And the way that we can interact with them is by querying them. So you're going to build this ontology, and this is all the things that can exist using that top level ontology. It's a big spider web. And then you query that ontology, and you're going to get a subset of the full ontology. When I say query, I mean you say, I have this thing, this entity, this continuant, this occurrence, and whatever they're connected to stays, and whatever's not connected, either directly or indirectly, goes. So just like we had an architecture framework and mission architecture framework, and a process framework and mission process framework, you have an ontology and mission ontology. So by querying the ontology, you have created your mission ontology, or gone from the things that can exist to the things that should exist. So you do this by inputting 1 or more subjects and objects, and then 1 predicate, and then it'll output 0 or more subjects and objects. And they're just things that exist. The subjects and objects are things that exist within the ontology, and the predicates are the relationships between those things. So then all of those query responses can be formatted as a machine readable data structure. Here's it starts with that resource description framework, those relationships, or XML, extensible markup language, and then you get to those object-oriented languages where you can do conditional logic a little bit better. If you have the combination of this and that, then do this. OWL and Protege doesn't do conditional logic very well. Finally, whatever your ontology was about, whatever content was inside of it, whatever query responses you wanted to structure, you populate your products with that. So this is how we can automate the generation of many of those products that we were talking about in the architecture framework. It is all integrated. It all comes together. Okay, I did say that this was going to be a little bit complicated. This is what part of that taxonomy might look like. It's what it looks like in Protege. So we have taxonomized here electronic hardware, and then circuitry hardware, and then that you have analog circuits and circuitry components. So looking at this, you have capacitor, diode, blah blah. And then under diode, here are all some of those more individualized. We are taxonomizing all of the possible components in a spacecraft. And remember, when we query the ontology, I'm going to say, well, I do have a laser diode and I do have Schottky diodes, but I don't have the rest of the stuff. So I have my mission ontology, just the things that I need. This is what those relationships, those predicates might look like in the ontology. So computer hardware has part circuitry hardware. Cool. Data process occurs in processing device. It's supposed to sound like a phrase, something a person can understand. Storage device participates in data process. So if I say that I have a storage device, or I say that I have a data process, I have queried the ontology with one or more subjects and objects. It pulls in the other subject and object based on this predicate. Okay? So let's look at an example. And this has to do with prognostic health management of spacecraft avionics and has to do with how radiation affects spacecraft. So it does get a little bit complicated. Stick with me here. So let's say that we have queried the ontology and said that we have a transistor, a complementary metal oxide semiconductor. Cool. This CMOS is a MOSFET, okay? Metal oxide semiconductor field effect transistor, all right? What we can do is say that this transistor is related to a software function. Okay, I have some software function, say to turn on a heater in the spacecraft, okay? So this MOSFET, this transistor, is a bearer of this function, okay? Now I know that this function is only going to happen if this MOSFET is functional, if it is still working. Well, I know that a MOSFET, by nature of what it is, has a gate, and that gate has a gate oxide, and this gate oxide is a dielectric layer. These are just things that a MOSFET has and is that are taxonomized within the ontology. The dielectric layer has a dielectric displacement field. So all of this is based purely on our ontology. And all we said is that we have a CMOS transistor. That's all we had. And we associated it with a software function. So if I am in an environment that has protons of a certain energy, a proton strike could ionize the gate oxide. And if that happens, it is equally going to break down this dielectric displacement field. These things happen at the same time. Well, if the dielectric displacement field is what's preventing the fault, the proton strike initiates that fault, and the fault manifests as a software error. So I know, based on just having this transistor that is associated with some software functionality, that if that transistor doesn't work, it's going to manifest as this error. All of this is accomplishable just by saying that I am in an environment that has protons, that I have a transistor that is associated with some software function. It might initiate a fault, and that fault might manifest as an error. So what just happened? What did we just look at? That was probably incredibly confusing, and probably a lot of people don't understand dielectric layers. If we do this for all of our hardware in the spacecraft, if we understand all of the different transistors, all of the different capacitors, what their software functions, what software functions are linked to which hardware, and we know the possible ways the hardware could fail based on the environment that the spacecraft is in, we know if a software error manifests, here are the 25 different things that could have gone wrong automatically if we use ontologies to do this. Prognostic health management is actualized if we are able to liken those, and we're actually building a tool that's going to be able to do this, because again, people should not be interacting with ontologies. People should be interacting with a tool that has an ontology in the background. All right, so to summarize, ontologies are taxonomies that have relationships between the categories. Okay, it's an agreement on usage. We are agreeing that these are the subjects, predicates, and objects that define how we operate as an enterprise. You have your ontology of all the things that can exist or happen, and the mission ontology is all the things that do exist or happen for your system or mission. We are developing an ontology that can do quite a bit of things automatically using these model-based systems engineering principles. I'll stop there. Any questions?
I got one.
Yeah.
Well, I guess first off, it makes a lot more sense on why we do what we do. I haven't really seen this before, and it actually makes a lot of sense when you said that thing on like how it goes wrong. So something goes wrong, you know exactly what could have gone wrong because of some error that happens. That's really cool. I hadn't thought about it that way before. But my question is, you said a little bit ago, relating ontologies and making sure that two ontologies can be combined. What's an example of when that would happen? Why is this between companies, between projects? Why would you not always start out with?
Okay, that's a really good question. So why would we not start out with the same ontology? Why does one ontology for the entire universe not exist? And it's an excellent question. There's a variety of different ways to approach this answer. Number one, there are things called reference ontologies and application ontologies. Reference ontologies in their taxonomies have at most one parent. You can only have one parent. A child can only have one parent. Application ontologies are more for a single enterprise or business. A business might do this specific to their needs, and that might allow you to have two parents for one thing. And so that having two parents immediately makes things not refactorable, meaning that it can't be combined with another ontology. You kind of broken a rule and you did it for the sake of your enterprise. And a lot of individual businesses have done that. There are examples of singular ontologies that are built from a main ontology. And the most popular one is the gene ontology. I think the gene ontology has been around since 2004. And I think it's part of something called the OBO Foundry, the Open Biological Ontology Foundry, where they have a hub and spokes model. So I didn't mention anything about definitions, but the way that these ontologies work primarily is through definitions. So if I say a fault is something that or which blah, 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 then I would say an induced fault, a subset of that fault, is a fault that or which blah, blah, blah. So an electrically induced fault is an induced fault that or which blah, blah, blah. So I think you can hear that you define fault, and then induced fault is a specialization of fault, and an electrically induced fault is a specialization of induced fault. Okay, so with the hub and spokes model, there was a central ontology at the very top that had a bunch of really rigorous definitions for the Open Biological Ontology Foundry. I think that's the acronym. The OBO Foundry, I know is what it's called. And then other ontologies branched off using that main ontology. So knowing that all of those definitions were agreed upon, remember, it's an agreement on usage, they took all those and then started getting more specific. The hard thing about this is that it is somewhat subjective. What we try to do as engineers is model truth. The cost of being wrong is too high. We care about what are facts and what are not facts. Facts are not subjective. There are not alternative facts. That's stupid. What we care, but when you get into really, really detailed engineering subject matter, people might disagree on certain aspects. There are two ways to measure the half-life of a neutron in space, and they differ by about 2.2 seconds. Which one is correct? We don't quite know yet. We don't understand why the measurements say that one is 2.2 seconds earlier than the other one. So ontologically, those could be modeled a little bit differently, and some people may not want to use that directly because they don't agree with it. But it's not because they're just rejecting facts. They just have a different interpretation, and we have not reconciled quantum physics with gravity yet. So It is somewhat subjective because it is based upon our most current understanding of the universe, and no one has put forth the effort to try and taxonomize everything yet. There are, I'll end with this. There's a group of 9 ontologies called the Common Core ontologies, CCO. They take the basic formal ontology at the very top, and then they spread out, and there's a bunch of different ontologies. And if you're a business trying to start an ontology, CCO is a good place to start. Just take that and run with it. So that's about as close as you're going to get to ontologies that define everything. If I ruled the world, I would certainly have us start making ontologies, because it's fact-based and it's a good way to make decisions. Like if I was defining government principles, happy election day, everybody, I would use this. I would model the system and then make decisions about what the model says. Does that answer the question? Probably a tangent or two.
No, sure, absolutely. Thank you.
Yeah, so it's not easy to combine ontologies, and people disagree. And that's probably the shortest answer for why there's not one centralized ontology. It's a good question. Any others? All right, let's press on. Almost done. Okay, so we're going to talk about concept representation using ontologies. So a lot of you watching are probably like, okay, cool, that's really advanced. I'm never going to touch that. Here is something that is a little bit more applicable that we in the Alabama CubeSat initiative do interact with on a frequent basis. Okay, so we're going to talk about a couple of things. Number one is verification by analysis. We have created a domain for verification by analysis. We just said these are the entities that exist within this domain. And what we have done is categorize things within an ontology and created relationships between them. It's the same subject, predicate, objects. Products reflect the concerns of stakeholders. Same thing, okay? But in technical analysis, we don't necessarily care about the taxonomy. We don't care that it is faults, induced fault, electrically induced fault. We just care what is the relationship between an electrically induced fault and an error, per se. So we care more about the relationships for a given domain. So we're going to talk about the technical analysis domain. And again, this is something that we've created. People could take this and make it their own, and they should. But what we've created is the domain ontology relationship map, or the DORM, per se. And we create domain knowledge maps as representations of analysis methodology. We're putting this online. We're building a tool to make these online, because making them in PowerPoint and draw.io is difficult. So what we're doing is verification of analysis and representation of the methodology using ontological principles. We are applying MBSE as a tool in the tool belt to verification by analysis. Okay? So we're going to describe a knowledge points methodology using a domain knowledge map. And that domain knowledge map is going to contain instances of categories defined by the ontology, with relationships in the ontology, and the map, this is that domain ontology relationship map, can be expressed as some n by n diagram. So to start with, these right here on the left, scalar parameter, array parameter, matrix, state, source, equation, modeling environment, entity, module, and modeling environment, those are entities, categories that exist within our domain ontology. For technical analysis, this is for the technical analysis domain, okay? So these are all the relationships between the categories in the technical analysis domain and themselves. You can have a relationship, subject and object are the same. So we read this from left to right and then down. An equation calculates a scalar parameter. A matrix parameter is an input to equation. A source provides a modeling environment entity. So we defined all of these categories. We know what they are. But these are all as we said, categories. They are not instances of categories. They are broad. So in a domain knowledge map, we are instantiating the categories one or more time to realize the methodology of a knowledge point modeling or calculation effort. Okay, so what do those instances look like? Here, let's say scalar parameter might be initial fastener stress. It's just one value. Array parameter, possible radiator areas. It might be some 1/n array. A state, thermal environment state. Source might be some document or handbook or textbook or paper that just got published. Some equation, you can define it however you want. This is just some that exists in our development and integration plan. A modeling environment parameter, that should say entity. Yeah, that should say entity. That's my fault. I didn't change it. This is something that exists inside of a modeling environment, but nowhere else. CAD is a good example, or mesh density is just something that is not necessarily a parameter, but it exists in the context of some modeling environment module, which might be some aspect of a modeling environment. You can conceptualize a MATLAB subroutine as a modeling environment module, and parameters exist within one or more modeling environment module, wherein the modeling environment is MATLAB. So these are the categories, and these are instances of those categories. Okay? So in a domain knowledge map, we are instantiating the categories. Okay? We are going to create these for every domain knowledge map, and every knowledge point gets a domain knowledge map. It might take several knowledge points and domain knowledge maps to fully represent the calculation of something important, like a technical performance measure or a key performance parameter. Okay, so what do those look like? Remember those colors that were on the domain ontology relationship map? These are sources. These are array parameters. This is an equation, this heat flux equation. This is a state, thermal environment state, scalar parameter, equation, array parameter. So this is what it looks like in practice. So it goes from left to right. A source is going to provide some parameter. Here's the variable for that parameter. This parameter is going to be varied by thermal environment state. So the thermal environment state is going to say, well, we have a hot and a cold thermal environment state. Okay, cool. So 1/2, one for each of the thermal environment states. This Earth surface heat flux equation, sure. It's just some equation that we're using, and this is with this input is used to calculate some Earth surface heat flux. Now notice that these two right here are ovals. This is just a representation that each of these has its own domain knowledge map. For this Earth emission heat flux, we're looking at the domain knowledge map, but this has its own domain knowledge map. So the ACSI thermal control team is providing this. They're effectively responsible for calculating or modeling whatever is in this domain knowledge map, but it results in this knowledge point. So this is a knowledge point, and this is a knowledge point, and this whole thing is a domain knowledge map. Read left to right, the visualization of analysis methodology using ontological principles applied MBSE. All right, let's take a look at another. This one is not the calculation, this is a model. So our team provides all of these knowledge points. Each one of these has its own domain knowledge map. So each one of these expands, nested. This is why we're building a computer program that can show this dynamically so that you can open and close stuff as needed so you can conceptually understand it. So all of these are inputs into a Simulink thermal resistance network. Simulink is the modeling environment module. Simulink is the modeling environment. This thermal resistive network is the modeling environment module. This time series is a modeling environment entity. It only exists in the context of this module. All of these knowledge points, the magenta or purple ones are matrix parameters, and these are array parameters. They all go into this thermal resistive network, and it models this component boundary condition heat flux array. which probably shouldn't be called an array because it's a matrix. But I think it's an array per thermal environment state. That's what's happening. So this is the representation of not a calculation domain knowledge map, but a modeling environment. All parameters must be either calculated by an equation, modeled by a modeling environment module, or sourced, provided by a source. So those are the only three ways that a parameter can come into existence. So to summarize, when we use things this way, it defines what parameters there are, which equations there are, where those parameters and equations come from, where the target values for TPMs are sourced from, where to start, it all goes left to right, the sequence of calculating it after you've started, and let's say you get a result that is not within acceptable levels or you want to change something about it, what can you change? Because you know visually what are the things going into this. I think a sensitivity study or analysis might be better done in a model, but it does tell you what your options are, visually representing the analysis methodology. All right, so to summarize, MBSE is about software-based tools. What we're doing is modeling in ontologies, in modeling environments such as Magic System of Systems Architect or Mimosa. We use SysML. We are communicating that common source of truth to both internal stakeholders, our own subsystem discipline engineers, and external stakeholders, our vendors, our contractors, our subject matter experts, the people who might pull the plug on a program. We need to communicate effectively to them, and the goal is model-based reviews. MBSE does not replace systems engineering. It's a tool in the tool belt. You are not applying MBSE wholesale to every part of systems engineering. You pick and choose the parts that it can be done best with. For verification by analysis, domain knowledge maps work really well. For integration, our integration diagrams, the activity diagrams that you saw in the model, those work really nicely. For requirements allocation and traceability, MBSE works really nicely. So those parts, it works really, really well. But there might be some other aspects, verification by inspection maybe, or defining the procedures for tests. Those maybe aren't places that MBSE is going to be great at, and you can do those outside, but it's about making decisions. It's not about producing documents. We have characterized this MBSE in terms of 4 pillars: architecture framework, process framework, modeling language, and ontology. The 3 pillars that Thomas Gasque defines are more closely related to the modeling language, but nobody's wrong here. It's just different ways of conceptualizing this. All right. All products that exist within an architecture framework are either artifacts generated by systems engineers from the integrated system model, or non-artifacts generated by discipline engineers from their discipline engineering, whether it's MATLAB or C++ or whatever, or SolidWorks, CATIA, pick your poison. The architecture framework defines all of the things that you could do, all the products you could make. Mission architecture framework is all the products you should make for your mission to ensure mission success. Likewise, the process framework, all the life cycles that you could choose from, all of the product categories you could make, all of the product maturation statuses, all of the reviews you could have, all of the stakeholders that you could have, which stakeholders must be at which reviews, which products are shown at which reviews. Process framework, which of those you should do, which life cycle you are in, what are your product categories, what are your maturation statuses, which products are shown at which reviews, which products are artifacts or non-artifacts at each review. That should be your mission process framework. You have your ontology, and then your mission ontology, the subset of that ontology that you actually care about. Okay. Pick what you're best at for MBSE, apply it to individual SE content. Don't apply it to everything. It's not a hammer. If you see it as a hammer, then everything becomes a nail. But in general, very powerful tool, helps us make decisions, avoids us from having to produce needless documents and spend 2 months creating a review data package when you can literally create it in hours. So that's all we got. Thank you all very much for your time. We appreciate it. Any questions? All right. Thank you all very much. We appreciate it. Look forward to seeing y'all soon.
Thanks, Michael.